In this screencast, we'll finish up our three-part series on Universality Theorem. So let's review the universal program, which we have developed so far as a proof of the Universality Theorem. So first, we extract the source code. Right, our program takes n plus 1 arguments. Then we encode the state as the Gödel number. Then set the instruction counter to 1. Then we check if the instruction counter is the length of the program plus 1. Right, or instruction counter is 0, which can happen if and only if we dispatch to the dispatch instruction contains a label that doesn't exist. Otherwise, we extract the BC component, the type of instruction, which is B, and C is the number of variable used in the instruction, then we get the R of U plus first prime, which allows us to get the value of the variable number C from the state. And then if L of U is equal 0, then we go to nothing, do nothing. Then otherwise, if the type of instruction is addition, we go to label A. If P does not divide S, which means that the variable C is equal to 0, we do nothing. Else we dispatch to minus if L of U is equal to 2. And if L of U is greater than 2, B is equal to 2, then we go to the line K, right, that contains the label used in the dispatch, right, because then the instruction must be of the form if V is not equal to 0, go to some label, and so K is the number of the line that contains that label, the smallest number. So let's see how we execute a no-op, addition, and subtraction. So if L of U is equal to 0, then we go to N, right? N is the label for a no-op or nothing. What exactly, how do we execute a no-op? We simply increment the instruction counter by 1. Set it to the next instruction counter, and then we go back to C. Which is, well, C can be construed as the continuation line. So should we continue, right? Let's check our label and see if label K now is 1 plus the length of the program, in which case we're done, right? Okay, so this is how we execute the no-op. Then now we let's talk about addition, right? So how can we execute addition? If L of U, right, or B, L of U is equal to 1, then we go to label A. Right, go to A, and what's going to happen at A is that we're going to multiply the state of the program S, the Gödel number, by P, which is the RU plus first prime, right, corresponding to the variable number C plus 1. A variable used in the current instruction. Let's take a look at a simple example to appreciate what's going on in this multiplication. Remember that S is a Gödel number. So let's say that S is equal to 63, and 63 as a Gödel number is encoded as 0201. Right, okay, this is the right, okay, so let's spell it out. 3 to the second times 7, right? 7 is the fourth prime number. Okay, 9 plus, okay, 63, right, just to convince ourselves that we are not doing anything wrong. So 2 is the value of x1, and 1 is the value of x2. And let's suppose that the instruction is x2 is equal to x2 plus 1, equals x2 plus 1. So we at the end, after this instruction is executed, the state the value of x2 should be set to 2. Right, so the fourth prime, right, which is the prime corresponding to the fourth spot in the state S, right, is 7. Okay, so we simply right, let's just review. The first is 2, the second is 3, the second prime, and the third is 5, and the fourth is 7, and so on. And computing primes, as we covered in the previous screencasts on the theory of computation, is a primitive recursive operation. Right, so we can write an L program. So the next value of the state is going to be, so let's call it S prime. S prime times P, which is 63 times 7. And because x2 corresponds to fourth prime, and this is equal to, as a Gödel number, is 0, 2, then 0, 2, right? And that's in turn is equal to 3 to the second times 7 to the second. Right, so we've increased the value of x2 by 1. Right? Okay, we've added 1 to that. Okay. And remember, we're dealing with only primitive operations in L, right? Everything, even the macros, as we covered in our previous screencasts, will compile down to primitive operations in L, like 4 primitive operations. And finally, subtraction. If L of u is equal to 2, I think it's 2. Yes, 2. 2, right, which is the number of the subtraction, the type of the subtraction. Go to m minus. So, all right, and at m, we just simply set s to be the floor of the division of s by p. We divide s by p. Right? Actually, technically speaking, we don't need integer flooring, although it is primitive recursive. We're just trying to stay consistent with the book, Computability, Complexity, and Languages, where this program is developed. But technically speaking, we don't need it, because if we get to this point, we know that p divides s. So example, let's go through an example. Let's take a look. Let's assume that s is 63. So in other words, the value of x1 is equal to 2 and the value of x2 is equal to 1. 0 is, the first 0 is the value of y, and then the second 0 is the value of z1, right, internal variable. Let's assume that the next instruction is a minus, right, x1 equals x1 minus 1. So after this is executed, our state should be 0, 1, 0, 1, because the value of x1 should go from 2, decrease from 2 to 1. Okay, so this is x1 and this is x2. So and it will okay, the second prime, which is p2, x1 is the second in our state. And in our variable list, so the next value of the state, s prime, will be 63 divided by 3, which is the second prime, and then floor. But flooring is not necessary. We're just staying consistent with the text of the chapter, and it will be equal to 21. And 21 is 3 times 7. Which, as a Gödel number, is exactly what we want, 0, 1, 0, 1. And so, as you can see, the value of x1 decreased from 2 to 1. So this is x1, and this is x2. Okay, so let's take a look at the complete universal program, and remember what we're proving. We're proving the universality theorem, which means that the function that takes the number of the program, L program, and a bunch of arguments to that program, right, x1 through n, xn, and returns the output of running the program on those arguments is actually primitive, is partially computable. Is partially computable. So, and the proof is this program, right? So we've essentially constructed the program in L, right? So the exit label extracts the value of y, which is the first component of state. well, the Gödel number S, which encodes the state of the program. So S sub 1 gets us the value, sets the value of in the first component of S to Y, because we're always returning Y. So this is our old friend BC, the type of instruction in the variable used in the instruction. Then this is the prime, P is the prime corresponding to a variable used in the instruction, and this is our dispatch. Okay, and so if it's no op, we simply increment the state of the program, and then go to C, back to that continue label. If it's addition, then we multiply S by P, and thus add 1 to the value of the variable used in the instruction, right, as we just covered. And else, if right, so, and if the value of P does not divide S, which means that that can happen if and only if the value of the variable used in the instruction, so C, variable number C, is equal to 0, so in which case we do nothing. Otherwise, it's subtraction, minus, and where is it? Okay, so it's over here. So we divide S by P, the value of the prime number corresponding to the variable used in the instruction, and then we go to N. Simply increase the value, the count, the instruction counter, by 1, and then check back the continuation state, right? Okay. And then the next thing is, if after dispatching to minus, while we check, we dispatch to the line number, the smallest line number, such that it has the label used in the instruction. Right, and if there is no such label, which is perfectly legal, then the value of K will be set to 0. Okay, so this is basically our proof of the universality theorem, that function that takes a compiled program number and of n arguments, and the arguments x1 through xn, and outputs the value of running the program in those arguments, is partially computable. So thanks for watching.